In our previous discussions, we have learned to evaluate the differential equation in the form mdx plus mdy equals 0 by treating it as the differential equations that we have previously discussed. So we solve for its solution, treating it as a variable separable dE or homogeneous or exact, inexact, linear, or Bernoulli. But sometimes there are certain differential equations which cannot be solved using all of those methods, even if you have tried all of those. So, in this discussion, we are going to solve a differential equation by a different method, and it's called by simple substitutions. Now, method is not new to us because we have done many substitution methods in integral calculus. So, as we know, when we perform substitution, we're going to introduce a new variable to replace an existing expression or a term in the given equation to transform it into another form so we can be able to solve the DE. So in this method, there is no general rule for finding effective substitution expression to be used. However, you have to, be familiar. So for example, in trigo, you have to be familiar with the differentials of the different trigonometric functions. So you have to study the form of the differential equation given, and an outstanding expression may be made with the basis of substitution. So all you will need to see is the pattern that you can see or you can see in the given differential equations. For example, we are given the dE. We're given the dE x plus 2y minus 1 dx plus 3 times x plus 2y dy equals 0. So here we can see that the expression x plus 2y occurs twice in the given equation. And I think it attracts our attention. And we can see here that there are no other expressions, there are no functions of x and y that stands out in this dE. So we can, if we are to make substitution, we can let x plus 2y be equal to a new variable, let's say for example, v. So when you replace this expressions here, x plus 2y, with the variable v, remember that you also have to express one of these differentials here, dx and dy, in terms of the other two differentials, because we are going to find the differential of this expression, just like what we did in integral calculus. So this is dx plus 2 dy equals dv. And then you decide, should you be expressing dy here in terms of dx and dv, or should you be expressing dx here in terms of dy and dv? So it's a decision that you will have to make, and it's up to you to decide which one should be done. But either way, it will give you the same answer. So let's say, for example, we are going to express, it's much easier if we are going to express dx here in terms of dy and dv. So dx is equal to dv minus 2 dy. And so substituting in our given differential equation, this x plus 2y here is now equal to v. So that's v minus 1. And our dx right there, this dx is equal to, okay, let me just underline so that we can see that our x plus 2y is equal to v. And our dx right here is equal to dv minus 2 dy. So substituting that one, dx, you have to make sure that you enclose that in a parenthesis because there are two terms right there, minus 2 dy plus 3, and then our x plus 2y is again equal to v, dy equals 0. And so we are going to distribute. So that's v dv. Okay, that's v dv minus dv plus 2v dy plus 2 dy plus 3v dy equals 0. So this is v times dv, v dv here, minus 1 times dv, that's minus dv, v times negative 2 dy, okay, so that's minus 2v dy, and then lastly, negative 1 and negative 2 dy, so that's plus 2 dy plus 3v dy. So simplifying our differential equation, grouping together, so that's v minus 1 dv. This is v minus 1 dv. And we can combine this one, negative 2 plus 3, that would leave us with v. So that would be v plus 2 dy plus v plus 2 dy equals 0. And so this is now a separable dE. We have v minus 1 over v plus 1 dv plus dy equals 0. And what do we do if we have a fraction? We divide. So by dividing, okay, v minus 1 divided by v plus 1. Remember that it's always the first term divided by the first term. So v divided by v, that's 1. V plus 1, so that's negative 1 minus 1, so that's negative 2. So simplifying, we have, or rather, this is v plus 2. That's v plus 2 right there. So we have to replace this. This is v plus 2. And so this is plus 2, so minus 3. So our dE is now 1 minus 3 over v plus 2 dv plus dy equals 0. And so upon integration, we have v minus 3 ln of v plus 2 plus y equals c. And what is v equal to? But v is equal to, okay, so since v is equal to x plus 2y, so we substitute, so x plus 2y minus 3 ln of x plus 2y plus 2 plus y equals c. So simplifying again, we have x plus 3y minus 3 ln of x plus 2y plus 2 equals c. And that is our general solution for our differential equation by performing simple substitution.